Hi everyone, Mr. Ricchini here today. Going to talk to you today about atoms, ions, and isotopes. Now there's a difference between all those things, but before we get started, let's just remind ourselves of what an atom is. We talked about this last time. We said that atoms are the smallest particle of an element that can actually still be the element. Remember, we talked about that. And we said that that atom is actually made up of three particles. They are the protons, neutrons, and electrons. Now that was all in the notes previously, but we have to know that to move forward. In that discussion, we talked about the fact that we have these particles, and if it's an atom, it has to be made up of protons, neutrons, and electrons. And I think we asked the question, well, what happens if we change those numbers of particles? Do they always have to be those numbers? And that's what I want to talk about first. Well, the first thing is looking at the protons. Now, each of these particles have a specific role that they're doing inside the atoms, and the protons are probably one of the more important ones. The protons, they're the positive particle that's found in the center of the nucleus, but their job is to determine what the atom actually is. In other words, if we change this, and we can change the number of protons, but if you change the number of protons, you no longer have the atom that you once had. It's now a new atom. For example, if we look at one of these squares on the periodic table, and here we have nitrogen, and nitrogen has 7 protons. And we'll talk more, you can probably figure out why, but we'll talk more about how the periodic table is arranged. But nitrogen has 7 protons. If I really worked hard, I could take that nitrogen and I could throw some extra protons at it, hoping to get one stuck, and maybe an extra one sticks to the nucleus. So I have 7 protons in the nucleus, and I throw a whole bunch more at it, and one little proton sticks. So now we don't have 7 protons, we have 8 protons. But that can't be, because the moment you have 8 protons, we don't have nitrogen anymore. It's now oxygen. So what that's saying is that every single atom in our universe is determined by the number of protons. If I go anywhere in the universe and I find an atom that has 7 protons, it's nitrogen. If I go anywhere in the universe and I find an atom that has 8 protons, it's oxygen. It's the number of protons that determine the identity of that atom. So that's a really important job, because the atom, the identity of the atom comes from the protons. But what about the electrons? Well, the electrons have a little bit different role, and we're actually going to get to this later on, but I'll talk about it briefly here. The electrons, if the electrons change, they're going to change not the identity of the atom, but they're going to change how that atom will actually behave around other atoms. In other words, we're talking about making compounds and combining them together in different types of bonds. And again, we're going to talk about bonding, and that's when we're really going to talk about this. But so if you change the electrons, what really are you changing? Well, if we change the electrons, think about this. It's not changing the identity of the atom, so it's still the same atom, but it's a charged particle. Remember, electrons are negative, and if we change the number of negatives that we have, we're going to throw that out of balance. Remember what we talked about, that the number of protons have to equal the number of electrons at the beginning. So any atom that we find that's just by itself, the number of protons and the number of electrons are going to be equal, making the overall charge a 0. If we start messing around with the number of electrons, they're not going to match up anymore. And that's important when it comes to bonding. And again, we'll get to that later. Now, when this does happen, though, we can't call them atoms anymore. So they do have a new name. And the name are ions. So if you change the number of electrons, we not only change the electrical charge of the atom, we also now change the name from an atom to what's called an ion. But ions and atoms have the same number of protons, they just simply have different numbers of electrons. And again, like it says here, we're going to talk more about this when we talk about bonding and the different types of chemical bonds that we can have. So, all right, so we talked about protons changing, we talked about electrons changing. What about neutrons? Well, that's really what today's lesson is all about, is understanding how to calculate stuff with these changing of neutrons. What's a neutron do? Well, when we talked about this in our last lesson, we said that neutrons don't have electrical charges, so we can add as many as we want, and it's not going to impact the electrical charge, which that has to do with bonding, so that's not going to do anything. If we change the neutrons, that doesn't change the atom, so that really doesn't do anything. So the only thing that a neutron really does, and it does really well, is it adds mass to the atom. That's its job. It adds mass. It's going to add mass to the nucleus. By adding more and more neutrons to that nucleus, the nucleus gets more massive, in fact more dense, and by becoming this more dense, more massive center, it actually builds a greater and greater and greater attracting force holding on to those electrons. Those electrons want to fly away. They want to go, but they can't, because even though they're moving so fast, the nucleus is so dense and has such a strong attraction to it that those electrons are forced to sort of stay circling around it. It's just like our solar system. Again, we go back to the Bohr model and the solar system, where our planets are traveling around the sun. But if our sun's not there, remember, our sun has tons of gravity and it's holding those planets in place. If the sun's gone, boom, gone. Our planet's just going to take off and go someplace else because there's no attraction toward the center of rotation. So the neutrons here, their main job is to help hold it all together. They help build that electrical charge. Now, when you change the neutrons, we don't change the electrical charge, we don't change the type of atom that it is. It's still an atom, but it's a little bit different now, isn't it? It has some more mass. So I like to say that it's a different version of the same atom. So it's still the same atom, it's just a different version of it. If you think phones or updates or on computers and software, I have an iPhone. So if you have an iPhone, right now my iPhone is at version 13.3. I just updated it. It was at 13.2. Is my phone any different than it was before? Slightly, right? There's a few little things that have changed, but it's still my phone, still has all my contacts, still has all that stuff. It's still basically the same thing. It's just slightly different because I've made a little change to it. That's what a neutron does. By changing the number of neutrons, it's still the same, just slightly different. Now, again, when we change the number of neutrons, we have to give it a different name. So we can't call it an atom. What we do call it is an isotope. Now, isotopes, all atoms are really isotopes. Every atom is a version of itself. Even if there's only one version, that's an isotope, right? So these different versions are called isotopes. All right, so let's get into how do we know about these particles. And we're going to talk a little bit about how to calculate the mass of these atoms and isotopes. And again, an atom is a very general term. And we said that if we have the number of protons determines what atom it actually is. So here we have a diagram of an atom, and we see we have positive particles, we have neutral particles, and we've got those little blue particles, those are representing electrons. And so if we look at this, we should be able to figure out, if we have our periodic table handy, we should be able to look at and determine what atom it actually is. How? Well, just look at the protons. How many protons does it have? It has 1, 2, 3 protons. So those 3 protons tells us that this has to be lithium. Lithium's the only atom on the periodic table of elements with 3 protons. So the next step is, how do we figure out the mass of this isotope or this atom of lithium? Well, again, this goes back to our last lesson when we talked about the different particles and the different relative masses that they had. And we said that the relative mass of a proton was a 1, the relative mass of a neutron was 1, and the relative mass of an electron was 0. So really, we only need to count the protons and the neutrons. So if we look real close here, if we add up all the protons and all the neutrons, what do we get? Well, the number of protons here is 3, and the number of neutrons is 4. So 3 plus 4 gives us a mass of 7. This is the mass of this particular version of lithium. So again, when we talk about atoms, we're talking in general, and when you say atom, it really is including all the different isotopes, but this is the mass of this particular version of lithium. Now, when we say isotope, What do we mean? Well, if you look up lithium, there are several different versions of lithium. And again, we already said this, but isotopes are just different versions. They have the same number of protons, but they have different numbers of neutrons. So here we have a different version of lithium, right? It's still lithium. Why? How do you know it's still lithium? It has how many protons? It has 1, 2, 3 protons. It's still lithium. But what's different about it? If you look real close, you'll notice that this lithium still has 3 protons, but it only has 3 neutrons. That's a little bit different than last time, right? So 3 protons, 3 neutrons, add them up. This time, this version of lithium only has a mass of 6. So it's basically the same. You see the number of electrons was the same, all that was the same. In fact, let's compare them. Let's look at them. So if we look at these 2 versions of lithium, we can put that line down the middle and we can just look exactly at what's different and what's the same between them. First of all, we know that the element for both here is lithium. Why? Because they both have 3 protons. What else do we know? We also know that they have 3 electrons. We can count them, 1, 2, 3, 1, 2, 3. And we see that the one on the left there has 3 neutrons and the one on the right has 4 neutrons. So really, the only thing that's different between these isotopes is the fact that one has more or less neutrons, and one, because of that, is going to have more or less mass. That's it. That's the only thing different. But both are lithium. They're both different versions, just different isotopes of the same atom. So I wanted to bring up this too. We've been talking about this relative mass of 1. And I thought it might be a good time to sort of bring up why this is 1 and where did this 1 come from and 1 what. We haven't talked about 1 what. We just said 1. It's a relative mass of 1. Okay. Well, when we say a relative mass of 1, we're actually talking in terms of an AMU, which stands for an atomic mass unit. This is the unit of measurement for mass in the atomic world. It's a unit that we had to create. So not me, but we, in general, speaking of the science community, they had to create the atomic mass unit, the AMU, simply because it was too small. You can't compare these masses. You can't look at these masses in terms of kilograms or grams or even milligrams. Those units are way too big. What is 1 AMU? Well, when they put this together, this is what the conversion that they did. 1 AMU, they said, was equal to the mass of a carbon-12 proton. Now, if you look at the carbon-12, you're going to figure out that there are 12 particles in that carbon-12 particle. So if we take a carbon-12 and we divide it by 12, we're basically, weird way around it, but we end up with, 1 as our answer. How? Well, 1 AMU, one of those protons is actually equal to 1.665402, I gotta look it up myself, times 10 to the negative 27th kilogram. That's a small number. That's in scientific notation. We should be familiar with scientific notation, but that's a very small number, isn't it? In fact, if you want me to write it out in long form, I will. There's what it looks like. That's how small it actually is. That's in kilograms. So kilograms, that's an incredibly small number. How do we do that? How do we even measure that? We can't. So, all right, so now if we look at the actual masses of a proton, the actual mass of a proton is 1.6726 times 10 to the negative 27th kilogram. Very, very small, right? Very, very small. Now, if you're saying why was the other number different, this is the average mass of all the different protons from all the different atoms that are out there. Last time we were looking just at carbon. This is the average for all protons. If we look at the average mass of neutrons, the average mass of a neutron is 1.6749 times 10 to the negative 27th kilograms. So these two numbers look very similar, and they should, because we said that when we compare one particle, the protons, to the neutrons here, that they were basically the same particle, and they were basically the same amounts, and they are. What about an electron? Remember, the electron we said was significantly smaller, and it doesn't have really mass that counts. And here's why. The mass of an electron, the average mass of an electron, is listed as 9.1 0.093 times 10 to the negative 31 kilograms. Now, to me, and maybe you're the same way, you look at that 9 and it sort of throws you for a loop, because you say, well, the electron looks bigger, right? Because it's 9 there instead of a 1. But remember, you have a minus 31. So if you understand scientific notation, you know that that number there, that's the exponent. So the bigger that minus number, so minus 31, the smaller that actual number is. Let me put it this way. Let's forget about the minus 31 and actually get it to minus 27. We're just going to move the decimal points a few places and get it back so that it's all the same. Does that make sense? We'll do it that way. All right, so if we look at it this way, it's now easier to compare all of them, right? So we look at the mass of a proton is 1.6726 times 10 to the negative 27th kilograms. The mass of a neutron, 1.6749 times 10 to the negative 27th kilogram. And now we can look at the electron, which is 0.00091 times 10 to the negative 27th kilograms. Now they're all in the negative 27th kilograms. We can look at that. They're all the same from the end. And we can see that now it's clear that the electrons are much, much smaller than the other two. But because the ends are all the same, we can get rid of the ends. So let's get rid of those and wipe all that stuff out except for the first numbers. And what do we notice now? Now, instead of talking about actual masses, we're talking about relative masses. And those relative masses is now measured in AMUs. This is where those relative numbers come from. It comes from the actual masses. So we took the actual masses, we compared them relative to each other, and now we have a relative mass. The mass of a proton is 1, the mass of a neutron is 1, the mass of an electron is 0. And last time we talked about why, even though the electron has mass, why don't we count it as mass? It's because it's really, really small. It's so much smaller than even the protons and the neutrons. We talked about that airplane, right? Talked about loading the luggage in and having the luggage go, and why the airlines weigh your luggage to know how much fuel they need to fly. And then you're looking out the window and you see that on one of those luggages you see a small ant crawling out, crawling on there and staying on there. You have a stowaway. Yes, you now have weight on the airplane that's unaccounted for, but we don't need to panic, because that little tiny weight is so insignificant compared to all the other masses of all the other suitcases. So we would really need a lot of them to even equal one suitcase. So you don't need to panic. All right, so how do we find information on the periodic table? We've sort of been using it already, but let's officially talk about it. So the periodic table, when we look at the whole periodic table, we can get all sorts of information out of here, but the basic information that you need to know is, again, what atom it is, how many protons, how many neutrons, how many electrons are there. And we can find that by looking at the periodic table. So we look at one square. Here we have silver, Ag. And the very basic periodic table is going to have a symbol and a couple numbers. That's it. Most periodic tables are going to have a lot more than that, but this is basic. So what are those numbers? Well, the first thing you have to understand is the number down at the bottom, typically underneath the symbol. It doesn't have to be there, but it's typically there. It's going to be the larger of the two numbers. That is your average atomic mass. This is the mass of all known isotopes of that particular atom. So it's not the mass of each individual atom or each individual isotope, but it's an average number. It's an average number. So if there's like 5 different isotopes for silver, then we average those masses up and we figure out what the average is. Now there's technically 2 stable isotopes of silver, but other atoms are going to have more and more different types of isotopes. What's the number at the top? Well, that's an important one, right? We've already been using that when we looked at lithium before. That number is called the atomic number. So the atomic number is the number of protons in that atom. So this number is going to be the same for every isotope that's out there. So every isotope of silver is going to have 47 protons. That's the atomic number. We'll talk more about how the periodic table is arranged, but right now, every square you're going to have an atomic number and an average atomic mass. The average atomic mass is the average mass of all those masses of all those isotopes, and the atomic number is the number of protons for every isotope. How do we write the information down about individual isotopes? So again, the periodic table is sort of a general collection of average numbers and average things for all the different versions of the atoms that are out there. But when we say isotope, we are now talking about an individual thing, an individual atom, or an individual collection of protons, neutrons, and electrons. That's what an isotope is. So typically when we want to write that or express that in a writing, the easiest way to do that is to write the symbol. So here we have the symbol W. You guys should know what that one is. That is tungsten, right? So we write the symbol, and then we're going to write two numbers. Just like on the periodic table, we're going to write two numbers, but these are slightly different. First of all, we're going to write a number on the left top side of that symbol. Here we have 184. What is that 184 for tungsten? That is the mass number. Now notice I did not say average atomic mass. The average atomic mass is only going to be found on the periodic table. This is the mass number. In other words, this is this isotope's particular mass. This mass belongs to this isotope. It's not an average number. This is the mass of this particular thing. That's it. At the bottom left, we have our atomic number, and that's going to be the same for any isotope. That's one way to write an isotope. There is another way, and sometimes it's written that way, so I'd like to show you both ways. It's actually pretty easy. The second way is we just simply write the name of the element or the atom, in this case tungsten, and then we put a number behind it. Again, you'll notice that number of 184 is the same as up above. That's the mass number. So either one of these is acceptable ways of writing an individual isotope. Okay? Now, how do we calculate out the particles of an isotope? Well, that's pretty simple, or it can be pretty simple. It's just, it is math. We do have to do a little bit of math here, but it's a simple subtraction. So let's put up here an example for us. Here we have Al, that's aluminum, and we see that we have a mass number of 27. We have an atomic number of 13 here. So the protons is going to equal the atomic number. Didn't we say that? The number of protons equals the atomic number. So the atomic number here is what? It's 13. So our protons for this particular isotope of aluminum is 13. Now, if our protons are 13, what about our electrons? To keep it balanced, right? The protons and electrons have to be the same. So our electrons are also equal to the number of protons. So that's also going to be 13. Now again, when we get to ions a little bit later, we're going to start messing around with those number of electrons, and that's different. Here we're talking about if we're just starting out, that by itself, before it starts to bond with anything, before it wants to make a compound, when it's just by itself, we know that the protons and electrons have to be equal to one another. All right, so that's easy. You got two numbers from one. The atomic number tells you the number of protons, tells you the number of electrons. What about the number of neutrons? Well, think about that mass number at the top. How do we get that mass number? The mass number is the protons plus the neutrons. Well, we already know what the protons are, and we already know what the mass is, so we just got to work backwards a little bit. To find the number of neutrons, we got to take the mass number and subtract the atomic number, or the number of protons, whichever way you want to look at it. So the number of neutrons in this case, for this particular isotope of aluminum, is 27 minus 13, which if we do our math, we find out that it's 14. So we have 14 neutrons in this particular isotope of aluminum. Now, if you look real quick at these symbols, I just want to point out one thing here. Notice protons is a lowercase p, neutrons is a lowercase n, and electrons is a lowercase e. Please remember that we've been talking about capitalization being important with the element symbols. They're important with other symbols in science too. We don't want to write these as a capital P, a capital N, or a capital E, because they can easily be confused by other things. For example, if you write that N as a capital N, it's no longer going to be neutrons, it's going to be nitrogen, and people are going to be confused with that, or you're going to misrepresent it, I should say, as something that it's not. Okay. One more thing I want to bring up before we do some practice with this is, how do we figure out what the most common isotope is? Because yeah, there are several isotopes of aluminum, there are several isotopes of lithium, there are several isotopes of all the atoms out there, most atoms, but how do you figure out what the most common one is? Like if you go out in the universe, you pick up an atom and you look at it, what's it going to be? How do you know what the most common is? Well, we've got to look at the periodic table, because that information is already there. We just got to know how to get it. It says the average atomic mass on the periodic table, you can find the most common isotope by taking that average number and simply rounding it to a whole number, and that's going to be your most common isotope. Let's go here to lithium and look at lithium again. Again, we looked at lithium a couple times. So here we have our lithium models, right? We see that on the left we have lithium what? We have lithium 6, right? That's the isotope lithium 6. Why? Because there's 3 protons and 3 neutrons. So 6 total particles in the nucleus. What about the one on the right? Well, that's lithium what? That's lithium 7. Why? Because there are 3 protons and then there are 4 neutrons. So as of right now, and there could be more, don't worry about that. Let's just look at these 2 particular lithiums. Which one are you going to find in the universe more often? Are you going to find lithium 6 or are you going to find lithium 7? Well, how do you know? Well, again, I gave you the square from the periodic table here, and we can see that the average atomic mass of lithium is 6.941. All we have to do is round that to the nearest whole number. So again, 6.9, that needs to round up, so that means that the closest whole number to that average number is 7. What's that tell us? That tells us that lithium 7 is the most common isotope of lithium. That's all that tells you. It doesn't tell you how much more common it is, but it tells you that it's not 50-50. It is more lithium 7 in the universe than lithium 6. How much more? Well, I'll tell you at least for now, but you don't have to worry about it. I'm not ever going to have you calculate this, but lithium 6 is found about 7.5% of the time, while lithium 7 is found about 92.5% of the time. So there is clearly a one-sided argument here that most lithium in the universe is lithium 7. All right, let's do some practice. So let's try to fill out these charts. What element is this? It's chromium. So this is the isotope for chromium. How many protons does this chromium have? 24. How many electrons? 24. And how many neutrons? Remember, this is where we have to do a little bit of math. How do we find it again? Take the mass number and subtract the atomic number. So in this case, 52 minus 24. And we get 28. All right, now try this one. Did you figure it out? It's gold. How many protons does this gold have and every gold has? 79. How many electrons does it have? 79. And how many neutrons? So remember, a little bit of math. 197 minus 79 gives us 118. Try 2 more. What element? That's chlorine. How many protons does this chlorine have? 17. How many electrons? 17. How many neutrons? 35 minus 17 gives us 18. The next one. It's what again? It's chlorine. But this is a different isotope of chlorine. So how many protons does it have? It still has 17. How many electrons? Still has 17. Neutrons are going to be different because it's a different version of this chlorine. 37 minus 17 is now 20. So these are good examples of 2 different isotopes of chlorine. 2 more. Here's an example of looking at a square from the periodic table. What element is this? It's one that you have to know. That's bismuth. So now we're looking at bismuth, and it says how many protons, electrons, and neutrons. Well, we're not talking about one particular isotope here, and if you have a question or in general you have that asked of you, how many protons, electrons, and neutrons does bismuth have, we can always assume that we are talking about the most common version, or the most common isotope of bismuth. So first thing we got to do is take that average atomic mass and round it to the next nearest whole number. So it's 208.98. 208.98 rounds closest to 209. So that's our mass number of the most common isotope. So how many protons? Well, the atomic number is 83, which means the electrons are also what? 83. Now our math, again, we cannot use 208.98 and subtract 83. We can't use that because that would indicate that we have half of a particle or part of a particle. So we have to use our rounded number. So 209 minus 83 gives us 126. The last one, let's write the isotope one last way. What if we write it this way? So if you have this presented to you and it says copper 64. Now, what's the symbol of copper? That's Cu. How many protons, electrons, and neutrons? Well, this one only gives you one number. Remember, that number behind it, that isotope written that way, is not the atomic number. It is the mass number. So that's the mass number of this particular isotope of copper. How are you going to find your atomic number? You have to look on a periodic table. So do you have a periodic table? Put this on pause, find it, and then write down the number of protons. Did you find it? Copper, all copper has 29 protons. That's the atomic number. The electrons are also 29. Our neutrons, we need to do a little bit of subtraction. So 64 minus 29 gives us 35. Now, if you still need a little bit more practice, what I would encourage you to do is, again, go to my website, my video page, and there you'll see Professor Dave. Professor Dave has a lot of cool videos out there, and his on isotopes really goes over what I just went over again, so you can hear it a little bit differently. Plus, he gives you some practice at the end, just like I did. So if you want some more practice with it, check out Professor Dave. It's on my website. I have a link for it there. You go to the video page and scroll down to the atomic structure unit, and just scroll through there until you see this image right there. But he can help you out and help you with some practice. Anyways, that's isotopes, and like I said, we'll come back to ions later, but hopefully you learned a little bit and you're getting better at calculating out all the different particles of an atom and isotope. See you later.